Our next speaker is Jaakko Kalliomaki. So welcome, Jaakko. Jaakko is currently working as technical product owner of high-rise elevator core technologies at KONE. He has got 15 years experience in high-rise lift engineering. So over to you, Jaakko, and we are looking forward to your presentation.
Thank you, Stefan. Sorry. Okay, I'm Jaakko Kalliomaki. I'm going to talk about a completely different topic. I'm going to be talking about 1927, a year which set the direction for traction lift engineering for a century. So a couple of points on historical context. So the turn of 20th century was a period of fast development in construction engineering techniques, and that sort of created a demand for higher lifts. And Kåpe mining hoists, which is also based on a traction sheave principle, was patented in Europe in 1887. And the first traction lift engine were introduced in America around 1890. But what was missing was a strong theoretical basis to quantify the needed traction, especially for single wrap elevators and undercut grooves, which were a novelty at the time. So in 1927, two Otis engineers, Fredrik Heymans and Axel Hellborn, published a book, Der neuzeitliche Aufzug mit Treibscheibenantrieb, that explained these new engineering principles. Coincidentally, at the same year, Hermann Donat from Germany wrote his doctoral dissertation über die Berechnung von Treibscheiben im Aufzugbau, without foreknowledge of Hellborn and Heymans' book. And neither of these landmark books have been published in English. So the key element, of course, in these books is rope traction theory. But as Donat writes in his foreword, the previous publications did not offer sufficient background, neither in form or content, for calculation of lifts with traction sheaves. So some of the basic assumptions that were set by Hellborn and Heymans when they were deriving the formulas for undercut grooves was the fact that the rope groove forms a non-elastic surface. The load does not change the cross-section of the rope, and the rope can be considered a smooth cylinder. And finally, the vertical pressure in the groove must be same in all contact points because the vertical wear of the groove is uniform. Donat, on the other hand, started from equations that were available for Kåpe hoists at the time, and after iterations ended up with similar formulations as Hellborn and Heymans. It is good to understand that the authors were critically aware of the limitations of their formulas from the beginning. So first of all, large undercuts. In large undercuts, the geometry did not anymore match the derivation. And importantly, this assumption of this uncompressible rope was something that was discussed by Donat in great detail, why he explained why this was sort of the safe assumption to be considered in the traction calculation. Important topic also in the books was the question about surface pressure. So first of all, Hellborn and Heymans determined that the groove wear is largely determined by the number of round trips the lift is making. And therefore, the lifts were classified in 4 groups based on their usage. And then the allowed surface pressure was then determined for each class based on experimental data. Donat has had some doubts about Heymans' pressure formula, but concluded that just more experimental data was needed in order to sort of make a final decision on that. Also, Donant was in the strong opinion that a rope slip alone could not explain the wear of the traction sheave, and proposed that potentially material changes in the traction sheave was also a contributing factor. However, all authors agree that the surface pressure calculation was important, and also that actually the rope safety factor calculation would be largely redundant in case the surface pressure limits would be followed. However, if we look at today's EN 8120, we see that the surface pressure limits have been abolished and replaced by rather complicated calculation of minimum safety factor. However, this minimum safety factor calculation ignores developments in rope technology, which then may lead to excessive groove pressure. Of course, in order to quantify the amount of traction, it's important to know how much friction there is between the rope and the groove. And Hellborn and Humans emphasize the difference between apparent friction, which includes the groove factor, and the actual friction coefficient. They claim that the reduction of friction is due to during slipping is largely due to lubrication, and that traction is dependent on the load due to the stiffness of the rope. It's interesting to note that their friction value was widely used in the lift industry at least up into the 1990s. Donant, in his dissertation, focused on studies of four separate topics. So the influence of surface pressure, lubrication, sliding speed, and surface quality to the friction. In contrast to Hellborn and Humans, he claims that the rope stiffness is not influential even with small loads. Lubrication can only be influential at the state of rest, because when the ropes are slipping on the traction sheave, the contacts heat up and the lubricants evaporate. In his tests, he found out this lower sliding friction coefficient and concludes that this friction value must be used in calculation. And his friction values were later used in German and European lift standards. Okay, so to quantify the amount of needed traction, you have to be able to determine the upper bound of acceleration and deceleration of lifts. So before the age of computers, it was convenient to have one load case that would cover both static and dynamic load cases, which led to the development of this kind of simplified dynamic factor, which applied with relatively good accuracy for most lift configurations. Important consideration between Hellborn and Humans and Donant was the fact that German lifts used mechanical braking at the time also during normal operation, while American lifts used electric braking. American lifts also had acceleration rates that were depending on the nominal speed of the lift, and by today's standards, the highest American values would be considered excessive. Donant did some field measurements and decided that the maximum sort of tolerable deceleration of a lift would be 0.3 Gs. And both concluded, based on slightly different analyses, that the properly dynamically dimensioned lift can be overloaded by about 30%, provided that the speed is low enough and the overload is not too frequent. And this is something that we see in today's A17.1 standard still. One topic that is only addressed by Hellborn and Humans is dimensioning of buffers, but it's a too important topic to be dismissed. So Humans had already been active in dimensioning of or designing of oil buffers before the publication of the Neuzeitliche Aufzug. And they state, first of all, that the decelerations above 2.5 Gs cause discomfort, and above 3 Gs are considered dangerous, based on what they claim experimental data. However, they design buffers to decelerate the rated load with an average of 1 G. And now this 1 G and these 2.5 Gs are something that we still see today's EN 8120 and A17.1 lift standards. But indeed, according Helborn and Humans, this 2.5 was regarded the safety limit, and this 1 G was essentially only needed to ensure that the ascending and descending bodies had a matching deceleration to eliminate the risk of counterweight jump. But then subsequently, based on Helborn and Humans, this 1 G limit for buffers has become an industry practice, and also later on impacted the requirements for safety gears as well. So, on the significance of Helborn, Humans, and Donnans. So first of all, making the dimensioning principles widely available acted as a major catalyst in a transformation of the lift industry. And one could easily compare to this importance of the invention of the safety gears like something like 50 years earlier. Also, traction lifts offered possibilities for standardization, which sort of further emphasized the importance and made this the introduction of traction shift lifts such a paradigm shift. As pointed out, some of the dimensioning principles have lived on to this day. And this is partly due to the fact that Humans and Donnan assumed significant positions in the lift industry in the following years, and therefore solidified some of their earlier engineering principles. Clearly, the principles have stood the test of time, but it's also important to understand that Donnan disagreed some of the points made by Helborn and Humans from the start. Also, some of the basic assumptions were not properly presented, at least not in scientific terms. It may also be that some of the original wisdom has been misinterpreted over time. But as lift industry will continue to see other paradigm shifts, it is important to challenge the old, but it's also important to understand the foundation, which is a pity why neither of these books have been published in English. Thank you.
Thank you.